So welcome back, dear students. So in the last class we had done about wave function. We have started the new chapter of quantum mechanics, that is quantum mechanics part 2. So there I had told about the wave function. Wave function gives us the space-time behavior of the particle, and it contains all the information regarding the particle, but wave function doesn't have any physical significance. The square of the wave function, that is psi star, where psi is the wave function and psi star is complex conjugate, that gives the probability. Okay, now I had discussed about various properties of the wave function. So these psi must be continuous, single value, partial. Each I had given examples. Okay, and psi x, del x must be square integrable. There are two other important properties, that is the square of the wave function, which I told gives the measure of the probability of finding the particle at a particular position. The magnitude of the wave function is large, where the probability of finding the particle is large, and vice versa. Okay, so now I'll start a new topic. The new topic is normalization and orthogonality. Normalization and orthogonality of wave function. Normalization and orthogonality of wave function. Okay, so what is this normalization? Normalization is a very simple thing I had done earlier also. Okay, so according to Max Born's statistical interpretation of wave function, the probability PR, okay, probability is denoted as PR of finding the particle, probability PR of finding the particle at any point R at a given time t is proportional to mod of psi square or psi star. Okay, that is PR is not equal to, but PR is actually proportional to mod of psi square or psi into psi star, that is psi into complex conjugate of psi. Okay, now PR is proportional to psi star, it's not equal to. So if you want to convert it to equal to, you must have a constant, which is called the proportionality constant, and finding the proportionality constant, is called as normalization. Finding the proportionality constant is called as the normalization. Okay, so now how you will find this? How will you find out the proportionality constant? Okay. Okay, so how will you find it? So now let us define PR. Okay, let us define PR or the position probability density, or the position probability density. Here the position probability density as PR is equal to psi star divided by integration of psi star psi or psi star d tau. Okay, that is integration over the entire space, that is minus infinity to if it was one dimensional, then it would have been minus infinity to plus infinity. Three dimensions, so I am taking the entire tau. Okay, now you see here, if uh, this is the thing, that is PR is equal to psi star by integration of tau psi star d tau. Okay, now here, now you know that integration of PR into d tau, again this is one. Okay, the integration of PR into d tau over the entire space. Okay, over the entire space, if you do the integration of the probability, that will be 1, because over the entire space from minus infinity to plus infinity, definitely the particle is present. So definitely you can find the particle somewhere in the entire space. So integration of PR d tau over the entire space will be 1. Okay, now you see here, if you put this value here, that is psi star by integration of this thing, what will you get? You will get this ultimately equal to 1. Okay, if you put this value, this ultimately you will get this equal to 1. Now another thing is that you see here that if here what you have to prove, you have to prove that PR is equal to psi star. You have to prove this thing. Now you see here, if you prove that if you choose psi okay, if we choose psi in such a way, if you choose psi in such a way that integration of the entire volume psi star d tau is equal to 1, then what will you get? Then you will get PR will be equal to psi star. Okay, PR will be equal to, so the proportionality constant is removed. Okay, the proportionality constant is removed. So then our problem will be solved. Then our problem will be solved. Then our problem will be solved. Okay, so how to do this? Okay, so you can do this by, if we multiply or divide psi by a constant. Okay, if you multiply or divide psi by some constant, so that integration psi star d tau will be equal to 1. Okay, if you multiply by some constant such that psi star d tau becomes equal to 1, then this will be solved. So if you take if you take psi as 1 by root of n, okay, if you take psi as, say 1 by say if you take some another wave function psi 1 as 1 by root n into psi. Okay, if you multiply or divide psi by a constant, So I am taking another wave function where psi1, that is another wave function. How? Here that psi1 star psi d tau will also be equal to 1. Okay, so and psi1 star will be what? Psi1 star will be, see, n is a real number, 1 by square root of n into psi, where n is a real number, Okay, so psi1 is equal to 1 by square root of n into psi, and psi1 star is 1 by square root of n into this will be psi star, okay. This will be psi star. So if you choose like this, then what will happen? Then let us see what will happen. So here psi1 into psi1 star will be what? 1 by n into psi star. Okay, psi1 into psi1 star will be 1 by n into psi star. Okay. So here you are choosing another wave function. Okay, psi1 and psi1 star are chosen in such a way, psi1 and psi1 star are chosen in such a way that this thing, that is in such a way that this thing this thing means that integration of volume integral of psi1 star into psi1 into d tau is equal to 1. Okay, so what will you get here? That is, here this thing, if you get, that is PR is equal to what? PR, then it will be psi1 into psi1 star. Okay, you see here that this is a different wave function. Okay, this is a different wave function but not different state. Okay, because why? Because the probability will be the same, 1. Psi1 star psi star d tau will be also 1, and psi1 star psi1 d tau will also be 1, this thing. Okay, so it is not a different state altogether, it is the same state only. So this will be psi1 into psi1 star integration of d tau psi1 into psi1 star d tau. Okay, psi1 into psi1 star d tau. Now what will you get here? Now you will get this psi1 into psi1 star into d tau is already 1. We have taken it in that way only, right? We have taken it that way only. And psi1 is what? Psi1 is again 1 by root n. Psi1 is 1 by root n, and psi1 star is 1 by root n. So this will be psi into psi star by n. Okay, so from here what are you getting here now? So from here you are getting now that, so now PR is becoming equal to psi star. PR is becoming equal to psi. The proportionality constant has moved out. So from here what you will get now? So here from here you will get now that this thing PR into d tau is equal to 1. So you are getting here psi star by n into d tau is equal to 1, or integration of psi star into d tau is equal to n. Okay, where n is called as the norm of the wave function, Okay, so now it's very easy to to normalize a wave function. How will you normalize any unnormalized? Okay, psi1 into psi1 star. Okay, psi1 star are normalized. Psi 1 star are normalized, psi star are unnormalized. Okay, so how will you normalize a wave function? How will you normalize a wave function? Any unnormalized wave function can be normalized. How the any unnormalized wave function can be normalized. How? Now by finding the norm. Okay, so you find out any unnormalized wave function, say psi is unnormalized, so psi star d tau. Okay, this will come something, some n or m or something. So if you find n, so you divide the psi by square root of n and divide psi star by square root of n, so that will be normalized. Okay, so for example here, suppose a plane wave. Okay, a plane wave, what is the equation of a plane wave? Suppose the wave function of a free particle. What is the wave function of a free particle? The wave function of a free particle is psi xt is equal to a e to the power of I kx minus omega t. This is a wave function of a free particle. So what will be its complex conjugate? Psi star xt will be I mean, this is a constant a, so it's no need to, it's a real function, e to the power of minus I kx minus omega t. Okay, so now what will you do? You will do this psi star, so this is one dimensional, so dx will be equal to 1. Okay, so now integration of this one will be what? Mod of a square into e to the power I e to the power minus I, so one a square dx will be equal to 1. Okay, so suppose it is the limit is, say say the limit is, say from it is valid from I mean the wave function is valid in between -1 and +1. So what will you do? So it will be mod of a square into 1 minus -1, so this will be 2, will be equal to 1. So a square will be equal to 1 by 2, so a will be what? 1 by root 2. So basically normalization means you have to find out this constant. So psi xt is equal to 1 by root 2 e to the power of I kx minus omega t is the normalized wave function, Okay, now comes your orthogonality of wave function. Okay, so now here what are you seeing? That this thing, that is psi star d tau. See here, this equation psi star d tau is equal to 1. When is this one? When they are of this psi and psi star, they are of the same state. Okay, but if they are not of the same state, okay, so let us consider two wave functions. Psi mxt and psi nxt. Okay, now in this case, minus infinity to plus infinity, psi mxt into dx, this will be always equal to 0. Okay, this will always equal to 0. This is called as orthogonality. But integration of minus infinity to plus infinity psi m xt into psi m xt dx, this will be equal to 1. This property is called as orthogonality of wave function. This property is called orthogonality of wave function. Okay, so this is called as orthogonality of wave function. Okay, now let us go to the next topic called as the operators. Okay, operators in operators, okay, and observables. Operators and observables. Okay, so what are these operators and observables? Okay, so now operator comes from the word operation. Okay, an operator is a mathematical rule. An operator is a mathematical rule. An operator is a mathematical rule that, acting on a function, gives another function. An operator is a mathematical rule that, acting on a function, gives another function. Okay, so now let us take an operator, say an O cap, an operator as your differential operator ddx. Okay, so acting on a function, what is the function? The function is fx is equal to x square plus 2x. Okay, so when this operator acts on this function x square plus 2x, what will you get? 2x plus 2. Okay, 2x plus 2. So this is basically an operator. Okay, now if an operator acting on a function, if an operator acting on a function gives back the same function, if an operator acting on a function gives back the same function multiplied by multiplied by some constant, then the function is said to be the eigenfunction. Then the function is said to be the eigenfunction of that particular. Then the function is said to be the eigenfunction of that particular operator. Okay, and the constant is known as the eigenvalue, Okay, so suppose some operator O cap is acting on fx, so it gives some constant alpha into fx. So alpha is the eigenvalue, and fx is the eigenfunction. Alpha is the eigenvalue, fx is the eigenfunction. Okay, so the best example is say d dx of e to the power x. What do you get? You get back e to the power x only. So here eigenfunction is e to the power x, and eigenvalue is 1. Okay, eigenfunction is e to the power x and eigenvalue is 1. Okay, so in quantum mechanics, each dynamical variable in quantum mechanics, each dynamical variable, example, position, momentum, energy, etc. Each dynamical variable, kinetic energy, potential energy, okay, is represented by an operator. Each dynamical variable is represented by an operator. Okay. Now if you write observable comes from the word observe. Okay, you can observe the position, you can observe the momentum, you can observe the energy, and this is operator. Okay, so observable is position has got operator what? R cap. Okay, R cap, or you can write R vector also. Then comes momentum. How you can write momentum is denoted as P cap. Okay, cap is not unit vector. Okay, so P cap you can write it as minus IH cut del x. Okay, or minus IH cut del y, or minus IH cut del z. Okay, or in short form, in 3 dimensional you can write minus IH cut del. Okay, so this is momentum. I'll explain how this particular thing comes. Then comes kinetic energy. Okay, kinetic energy is what? Kinetic energy you have studied. Actually, it is E square by 2m is the kinetic energy. So if you write it, you can write it as minus h cut square by 2m into del square. I have done this in the first part of quantum mechanics, in the group velocity, phase velocity, all these things. So this is what? Minus h cut square by 2m into del 2 by del x2 plus del 2 by del y2 plus del 2 by del z2. This is the kinetic energy operator. Then potential energy. Potential energy, very simple. V cap r vector is equal to V of r vector, you can write. Okay, total energy, that is kinetic energy plus potential energy. Total energy is given as E cap is equal to IH cut del T. Okay. Then comes your Hamiltonian operator. Hamiltonian operator is given as H cap. This is written as kinetic energy plus potential energy. Okay, so this will be equal to minus h cut square by 2m into del square plus v r vector. Okay, angular momentum. Angular momentum operator, how you can write? L vector is equal to minus I h cut r vector cross del vector, means angular momentum r cross p, right? Angular momentum is basically what? R cross p. Now p is what? P is minus I h cut del vector. This is del vector. Okay, so this thing. Now let us describe how this thing comes. Okay, let us describe that how the quantum mechanical operator P is minus I h cut del del x minus I h cut del del y, how that thing comes. Now I'll describe that. Okay, so for a free particle, okay, for a free particle, what is the wave function? For a free particle, the wave function is, as I wrote there, psi is equal to psi is equal to a e to the power of I e to the power I kx minus omega t. Achha, now let us do del psi by del x, that is partial derivative with respect to x. Okay, so what will you get here? Del psi by del x will give you I k into a e to the power of I kx minus omega t, right? So this will be I k into psi. Okay, so now px is what? Px is h cut k. This also I have proved in the first part of quantum mechanics, in the group velocity, phase velocity, that is momentum is equal to h cut k. If you don't understand here, you see that, you will understand. Okay, so it's nothing but p is equal to h by lambda. Okay, so h by lambda is what? H by 2 pi into 2 pi by lambda. So h by 2 pi is what? H cut 2 pi by lambda is k. So h cut k. Okay, so or here so here p is equal to h cut k. Okay, Achha, so here if you multiply this equation by I minus I h cut. Okay, so minus I h cut del psi by del x. If you multiply this, so what will be minus I into plus I, so plus, so h cut k into psi. So this will be what? P, so since it is in x, so px into psi. So therefore here px will be what? Minus I h cut del del x. Okay, minus I h cut del del x. So similarly you can prove py is equal to minus I h cut del del y. Okay, pz will be minus I h cut del del z. Okay, so definitely in three dimensions, what will you get? P vector will be p vector sorry, rather p cap, momentum operator, minus I h cut del. This will be in three dimensions. Achha, now comes the kinetic energy operator. And regarding position, there is nothing to do. Position is, you can write r cap or x cap, comma y cap, comma z cap, you can write. So in position you don't have to derive anything. Achha, kinetic energy operator, how will you write? Achha, kinetic energy is what? Kinetic energy is p square by 2m. Okay, p square by 2m. Now p the p is what? P is already, you know, that minus I h cut. So minus plus. So I square is minus. So minus h cut square by 2m into del 2 by del x2. Okay, this is the thing. Achha, now again psi is what? A e to the power of I kx minus omega t. So here del psi by del t will be what? Minus I omega into a e to the power of I kx minus omega t. So this will be minus I omega into psi. Okay, Achha, now minus I omega into psi. Okay, so if you multiply this I h cut del psi by del t, if you multiply this equation on the both sides, you multiply it by I h cut. So what will you get? I h cut del psi by del t will be equal to minus I omega into I h cut into psi. So this will be what? My I square is minus, so plus, so h cut omega into psi. Now what is h cut omega? H cut omega is energy, E into psi. So therefore E, operator E will be what? Will be I h cut del t. Okay, operator will be I h cut, energy operator will be I h cut del t. Okay, this is this is the energy operator will be I h cut del t. Okay, the energy operator, this will be the total energy, and kinetic energy operator is this only. Kinetic energy operator will be this minus h cut square by 2m into del 2 by del x2, or minus h cut square by 2m into del square. Okay, this will be the kinetic energy operator, and this will be the total energy operator. E cap is equal to minus I h cut del t. Okay, acha